Hi everyone, welcome to my channel. If you're new to this channel, kindly subscribe and hit that notification button to always get my updates. Please also leave a comment. In this tutorial, we'll talk about how we can use symbolic Python, which is the Sympy package, to solve different problems in the calculus. And within this calculus, first of all, we'll talk about derivatives. We'll also talk about how we can integrate double and triple integrals. We'll also talk about some partial differentiation, and then we can end up looking at different problems in how we can find limits of different functions and how we can expand different functions. So without wasting much time, let's get to the point. So what we are going to do is to begin by importing our package, which is the Sympy. So I'm going to say from Sympy import everything, because I need everything that is within the Sympy, and also I'm going to turn on init printing Unicode, use Unicode to be true. Alright, so this is going to help us in printing. So if I run this, we have already now our tools installed or imported within our working space. So I'll just get straight to the point that if you want to differentiate any function within Python using the Sympy package, you only use a command which is the diff, standing for differentiation. So let's try to look at how we can do the first derivative. So to do this, we are just going to first of all declare our symbols. So I'm going to say x, y, and then z. These are symbols. Again, symbols is within the Sympy. So this is x, y, and then z. So when you use now x, y, and z, Python will know that these are symbols. So right here, I can proceed and then say, let's say we need to say y is equal to x power 5. All right. So when I go down and then try to print y, then this is going to give us some equation. Y is equal to x power 5. All right. So because x now is taken to be as a symbol, that is why Python is not complaining. So let's try to go ahead and differentiate y. So I'm going to use a function diff of y. So if I do this, then it's going to give me power 5. All right. So this means that the function x power 5 has been differentiated, and then we are coming up with 5x power 4 after differentiation. All right. So this is how we can use the diff function to differentiate different functions. And then with that, I can as well give another example with diff, for example, sine of x, all right, and then multiply by tan, let's say again, cos of x. All right. So when we do this and run, we will get minus sine squared x plus cos squared x, which is the derivative of the product of sine x and then cos x. So basically, this is how we can use this diff function to differentiate. The same thing would happen if I wanted to maybe differentiate something like diff of x power 3, let's say, plus 2 times x power 2, and then minus 2 times x, then plus 1, which is some polynomial function or equation. And then if I differentiate that, this is what will come up with. All right. So basically, if you're differentiating anything, this is how we can use the diff function, which is under the Sympy. All right. So let's proceed with another another function or another example how we can try to apply Sympy within the derivative. Likewise, we can try to differentiate logs. The same thing I could do diff of a log of x with I can declare with respect to x, and this means also I'm differentiating once. Alright, so if I do that, then this is going to give me 1 over x. So log x is taken as natural log of x, so which comes out as 1 over x. So if I wanted, for example, to differentiate this 3 times, then I would simply repeat x many times as I want to differentiate. For example, x, and this would mean that I'm differentiating this 3 times, and this would give me 2 over x cubed. Alright, so the same thing I would do if I wanted to differentiate this 3 times. Instead of writing or repeating x 3 times, I would just write x then comma, which means I'm differentiating with respect to x, but then a given number of times I want to differentiate, that is 3 times, and then if I do that, I'm getting the same answer. If I wanted maybe to differentiate 5 times, I would either write x 5 times, or just to have x with respect and then to have 5 as the number of times, and so that would give me the derivative. Alright, so this is basically how we can try to differentiate a given function many times, multiple times, with respect to a certain variable. Alright, so we can move into partial derivative, and like I said up here, I declared already x, y, and z, multiple variables, and we have already them imported within our working space. So let's try to see how we can differentiate partially. So I'm going to make this as a title, as partial derivative, and change this to heading. Alright, so let's look at partial derivative. So I can call, maybe this is heading 2, and that is a heading. So if I run that, we have partial derivatives. So how can we do that? We have already our x, y, and z imported. So I'm going to write an expression and say this is equal to maybe some exponential function. Let's say exponential of some product of say x squared, alright, times x, maybe times z. Alright, so that we have an exponential which is in terms of 3 okay, this should be y, terms of 3 variables, that is x, y, and then z. So if we try to just call this again expression, we have, oh, what is happening? X squared times y, where is y? Yeah, because y, it is substituting for y as power 5 up here, so it is still remembering and then doing the substitution right here for our y. But anyway, in any case, we can remove, since I wanted to demonstrate for different variables, we can do it like that, or we can just change y to another variable, but we can go with this. So this is x power 2 then times y, but from up here y was set to be x power 5, and then that is why it is substituting it now directly in the position of y with x power 5 and then giving us x power 7 z. Alright, so let's try to differentiate this with respect to x, y, and z, but definitely y is now out. So we are going to say differentiate, alright, our expression. Then we can choose first to differentiate with respect to x, and so if I do that, then this is going to give me, when you differentiate the power, which is now a combination of x power 7z, we are only interested in differentiating x, so that will be 7 in front x power 6 z, which we see right here, and then the exponential remains as it is. All right, so the same thing if I wanted to just differentiate with respect to z or z, I would just have this as z, and then when I do run this, this gives us x power 7 because z becomes 1, and then exponent x7 z. All right, so now let's see if we wanted to differentiate everything maybe with respect to all the variables we have. Let me just modify my expression just a little bit right here. I'm just using the same expression but a little bit modified. So let's say we have a case where you have x squared then plus maybe z squared as well. All right, so you have something like that. So how can we differentiate with respect to both variables x and z? So in that case, we need to declare all the variables we need to differentiate. So I'm going to say diff differentiate of expression 1, but now with respect to x, and then with respect to z. And then when I run this, this is going to give me 4xz exponent of x squared plus z squared. So in this case, it differentiates with respect to z, and then it differentiates with respect to x, and then we come up with 4xz exponential of x squared plus z squared. So this is about partial derivative, and we can actually also try to represent such a derivative partially by printing it out so that we can see clearly what it means. So to do that, I'm going to say, let's call this maybe answer, and this is equal to, I'm using derivative of the expression. So I'm just trying to print it out then with respect to x, y, and then z. Okay, so when I call this back again answer, it will give me partial derivative with respect to x and z of x squared plus z squared. So this is what we have been dealing with. All right, and then so basically that's what it is. So when you proceed, let's see basically another example what we can come up with. So if you had separate variables, different variables or different functions, still you treat it in the same way. All right, so now I can move to something to do with integration. We have looked at so far how we can differentiate any function. Just use declare the symbols, differentiate the function with using the diff function, and then you get your derivative. And partially you can differentiate the functions as well in different variables, as we have seen in part 2. And right now let's try to look at integrals or integration in the two forms. So I'm going to say integration. All right, and then I'll make this as my heading, and I'll call this just number 3. So integration. So when I run this, we have our integration. So how do we use Sympy to integrate? All right, we can use Sympy to integrate almost each and everything using different functions that are within the package. So I'm going to say, first of all, I'm going to use the integral function, which is the integral. All right, and then try to print this one symbolically, and then I have 3 times x. So this is maybe, let's say, squared. Okay, but we can say this is going to be with respect to x. So if I try to display this, this is going to give me integral of 3x squared dx. So I'm using this function integral. All right. So let's now proceed to see how we can integrate. All right. Integrate the actual function which you have seen up, or which you have seen here being represented symbolically. In that case, I'll use the function integrate and use whatever I want to include in, which is our function 3 times x squared, all right, with respect to x. All right, so if I do that, then this is integrated. As you can see, we have 3 in front here. If we integrate x squared, we increase its power by 1. That goes to x cubed, then divide by the new function by the new power, which is 3. So the 3 will cancel, and then we'll have x cubed. All right. So if you wanted to evaluate that, that is maybe if it is definite, still I would simply say integrate 3 times x squared. Then I would have my with respect to, and then from let's say 3 to 2. All right, or 3 to 2, that would be in the reverse. So basically from the lower limit, which is 0 to maybe 2 or 1, and just keep it like that. So when I run this will give us just 1. All right, because it will be the integral will come out as x cubed, then evaluate it at 0 and 1, which gives us 1. So let's try to continue with just some symbolic representation of some different variables. So another example is if I want to present integral of, let's say, sine of x. All right, and then this is going to be evaluated within an interval of a to b. So I'm going to have with respect to x, then a to b. All right, so if I do this and then run this, yeah, because a is non-defined and then b is non-defined, because these are symbols. So I would just include them maybe up here and say a, b. These are called also symbols. All right, and then I have them in quotes, ab. All right, so if I do this and run this again, it will have solved the problem. So usually Python gives errors that you can understand if you read them. So we have integral of sine x, and then with respect to x from a to b. So this is how you can represent any integral that you want to integrate. And if it was in terms of, maybe say you are integrating from infinity to some value, let's say this is, let's call this tan, from negative, say, infinity to positive infinity. In this case, we use the O's, double O, to represent the minus infinity, and then the positive infinity to be just represented by O, just because these O's, when you combine them, they look like infinity. So this is how Sympy regards the infinity as. All right, so if I try to run this, it will give us from positive infinity to minus infinity, or the other way around, of tan x dx. All right, so now let's try to look at one more example about how we can integrate a trigonometric function. And so I'm going to say integrate, all right, of cos of x, all right, then let's say over 4 from with the limits of, say, pi over 4 to pi over 2. All right, so if I do this and I try to run this, this will give us the answer like this. All right, a very simplified answer to this, as we can see. So the same thing you do for other functions. If we had like integrate, let's say, natural log of x, okay, then from some numbers of some limits, let's say from 1 up to 4, all right? So this would give us something like -3 plus 4 log of 4. This is natural log of 4, all right? So this is what we have, and this is how we can integrate any function. Please, you can try out any function with any complication. So finally, let's try to say if I wanted to integrate, all right, a certain function. Maybe we can first write the function up here, and I'm calling this, say, okay, let's just integrate it. Okay, let's just integrate this function, integrate a certain function which you can look at as let's say 2 over x plus 4, all right, and then brackets, which means we need to multiply here, and then x squared, then minus 16. As you can see, this integral, all right, let's first even print it out like integral, right, of this expression. So when we do this and we want it to be from maybe 0 to 1, so if I do this, all right, so there was just an extra bracket somewhere here. So let's try to see how we can integrate such a function, all right? We know that this one goes into partial integration. As you can see, we can modify what is down here, or I can even reduce this maybe to make it 3 to be different from the other one. Then the rest, you can see this is a difference of 2 squares, can be expressed in terms of x minus 4 into x plus 4, and then the rest can be we can find the partial fractions of this, and then we can integrate it. So let's see how we can integrate this. So now let's try to integrate it now and evaluate it with the limits of 0 to 1. So I'm just going to copy this expression and then use the integrate function, paste that, and then this is what we have. So when I plus run, this is going to integrate this using the method we know, which is the partial fractions, integration by partial fractions, and then we have -4 log of that, and so on and so on. This is actually the answer you would get if you integrated or you tried out with your calculator and so on. So all right, so this is how we can integrate different expressions. We can look at one more. If we integrate let's say 5 over 5, let's say we have this 5 plus x, all right, everything over x squared plus 1, all right, and then this is going to be with respect to x, and then from say 1 to 3. All right, so if I run this, integrate, oh, it's not defined. I meant integral. So this is supposed to be integral because integrate goes with small I, so this has capital I. So if I run that, this is what I want now to see, how we can integrate this, and then from here we can try now to evaluate it based on the limits 1 to 2. So I'm just going to copy the expression above here and then simply use the integrate, right, with small I of this, and then we know that this at least it has some part which is of turn substitution, and then another part which is of natural log, because when we separate this into partial fractions, it will be like x over x squared plus 1, then plus another part which is 5 over x squared plus 1. So the first part would go to like natural log what is up, x is like the derivative of what is down, so a half of that, and then the other one will be of tan substitution. So if I run this, we'll have actually our final answer like this. So the log O, which is the natural log I mentioned about, is occupying this part, and then the tan substitution, which would be for the 5 over x squared plus 1, which is the last part, is the one that gives us this answer. All right, so this is basically how Sympy can be used to integrate. So with having said that, all this, let's try to continue and look at some different integration, like multiple integration. So I can call this one for that is multiple integration, and then we can move on further to another part. So I can call this one heading for multiple integration. So how do we integrate multiple integration? So you have seen this multiple integration several times, so the same thing applies. So I'm going to say integral of, let's say, a certain function, which is maybe exponential to make it easier, maybe minus say x squared, and then this is times let's say, I already explained, I think I already used maybe some other variable, let's say t squared. I'm going to define t squared as a symbol as well, t squared. So I have to declare t here. I wish I did that before. So t is symbol. Since it is 1, it's going to be capital symbol. All right, so this is t, and so this is what we have, integral of that. And so since I want to integrate from some limits, I'm going to have maybe my brackets, the first bracket representing the limits of one of the variable, let's say for x. So this is going to be x, and I want to do that from minus infinity to positive infinity. And then the next one for t, again I'm opening new brackets for t, and this is going to be, let's say, from 0 to maybe 5. All right, so if I do this, I hope I have enough brackets here. Yes, so and I run, this is going to give me something like of double integral. So from 0 to 5, integrating minus infinity to positive infinity of this dx and then dt. All right, so you can see that we're integrating the outer one. This we have the dt first outwards, and then we have the inner integral, which is of the x. So again, if I wanted to integrate this, I would just copy this and then use the integral function to give us infinity. All right, so that's the answer that is coming out because of this. But if I wanted maybe to maybe change slightly, -1 and then maybe to 2, and then run this again, it will take its time and then finally give us some expression right here. So that's what we have. Now let's try to finally try to represent maybe a triple integral in the same way. I'm just maybe going to copy this just to add in one more stuff. Again, I can add in maybe one more variable, call it r. And so since it is symbols many, this is going to be symbols now. I'm just changing this slightly, and then we'll have r included here. I can run this again, and then when we come here, so I can just add on something here as r maybe cubed or just r. All right, and so when we have such a case, we have, let's keep all this as minus infinity, the same limits maybe. All right, so positive infinity, and then finally we have one more bracket here for r, then which is also from minus infinity to positive infinity. Just to modify a little bit, I can make this one addition plus, and then also the other one plus. All right, so this is what we have basically now, and then if I print this out, it will give us something like that of double integral. So in the same way, if you wanted to integrate, you would just use this function, integrate, and then of this big expression. Now, some people requested how to show them how we can work with limits. And so with that said, I'm going to call this one my heading 5, limits in calculus, how you can find limits of a certain function. All right, so let's look at these limits. So how we can solve limits? We can solve limits using the limit function, as simple as that, and then we include the function which is, say, fx, and then if it is in terms of variable x, then and then what it is tending to. If it is tending to 0, then we can have tending to 0, just writing 0 as that. If it is tending to, say, positive infinity, then we use, as we have seen, double 0. And if it is tending to negative infinity, then we can have that this is tending to minus infinity, just like this. All right, so let's see how we can approach some of the examples we have here. So I'm going to have like limit of a certain function. Let's say 3x, let's say 3x. all right, 3 times x, then plus 1, and this is in quotes and in brackets, then divided by maybe x minus 1. all right, and so with this, then I need to declare x, and then x is tending to 0, so it's becoming very small, that it is towards 0. So when you look at this expression, 3 times a very, very small number, that one almost tends to that very small number, if not 0, since x is just getting to 0. So we have basically the upper expression getting to 1, then over what we see down here as minus 1. So if I run that, that should give us the answer as minus 1. All right, so we can look at another expression. Let's say sine of 4 times x. all right, and then this is divided by let's say x. all right, and then we have x tending to 0. So when you look at this, when x is becoming so small, all right, we remember that for sine of a very small angle tends to that very angle. So this would the upper expression, or the upper term, would reduce to basically 4x, which is now divided by x, and then we can see that what survives is just 4, and then when x is tending to 0, so when I run this, this will give us just 4. all right, the same, let's look at one more example. If I have a limit of x squared, all right, plus maybe 4 times x, then minus 10, right, when we have x and then tending to 0, this is going to give us just minus 10. all right, so the other parts will vanish, and then we have just minus 10. So how about if we have a certain variable but tending towards infinity? In that case, we can demonstrate that with an example here. Let's have let's say x squared, then plus 4, then this whole expression over x say squared, then minus 10. all right, so in the same case, we have x, but this time tending to infinity, or just positive infinity, and this is what to say. So in this case, how we can quickly identify what we have here, we could see that if you first of all, try to analyze the expression by dividing through by the highest power, and that is x squared. So up here we'll have just 1 plus 4 over x squared, and then down here we'll have 1 minus 10 over x squared. So when x is becoming or is tending to positive infinity, we could see that 4 over x squared over a very big number square that would go to 0. So we'll basically have like 1 over 1, which will give us just 1. So if I run this, you can see that we have 1. All right. With that, let me go to how we can expand functions using Sympy. All right. So we have series expansion, and maybe that will make the end of our video. So series expansion, so I can just have this as our heading number 5. Right, so how do we expand functions, be trigonometry, be exponential, and so on? So first, what we need is to create our function or write down our function. So I'm going to say our expression is equal to, let's say, exponential of just x, which function all of us know. And then from there, when we create our expression object, then we can use the series function to expand that function. So I'm going to say expression, then dot series, then it is in terms of x, so we have a series x in terms of x, and then when I run that, that will give us up to the order of 5. All right, so this is giving us 1 plus x squared plus and so on. All right, so this is how we can expand. So let's say we have another example, and I'm looking at sine of just x, and then the same thing I can do if I want to expand sine x. So I'm going to say x dot series in terms of x. All right, and so when I run this, this is going to give me an expansion of the series, which we definitely all of us know. All right, so this is how we can expand functions. But if you basically want to exceed this 5th order power, then you need to include in the power. All right, so with that said, I'm going to include in the powers from, say, 0 up to a certain number or a certain order. So I'm just going to demonstrate this. If I wanted, say, the power, then I'm going to say from 0 maybe to 10, expand up to 10th order. Right, so when I do that, then it will go up to the 10th order and so on. So if I want maybe up to 20, then it will expand it up to 20th term. All right, so this is what we have, and this is how you can expand any function in Python using the Sympy package. All right, so basically that's what you can do, and it's very easy, as simple as that. Let's try to look at one more example. That is expansion of tan of a certain function. So I'm going to call this x2 equals that, and then we'll have tan in terms of let's say x squared. All right, so when you create that function, then I'm going to expand it, x2 dot series series, and then of x, then we need up to maybe 7th term. So this is what we have. So if I run this, this is going to give us these 3 terms. So if I just maybe keep it as a default, this is what we have. All right, that's it. Thank you so much for watching. Kindly subscribe and watch also my other videos about different tutorials. Thank you so much.